All right, welcome back. Today, we're jumping into a super fun, really satisfying little coding puzzle. How do you take a simple string, just numbers and parentheses, and, like magic, turn it into a full-blown binary tree? Come on, let's get into it.
So here's the puzzle, right in front of you. On the left, you've got this string, 4, 2, 3, 1, 6, 5. And on the right, that's the binary tree it's supposed to become. The big question is, what's the logic? How do we write a program that can actually build this structure just from that text?
Okay, so to crack this thing, we've got to start with the basics. We need to really understand the blueprint, the rules of the game for this weird string format.
And you know what? The format itself gives us a massive clue. It's always a number, that's our node's value, and it's followed by these parentheses. And here's the key. Each set of parentheses contains a complete child tree. And guess what? That child tree follows the exact same pattern. See where this is going?
So, it really boils down to 3 simple rules. That first number you see, that's your root. The first block of parentheses right after it, that's always, and I mean always, the left child. And if there's a second block of parentheses, well, that's got to be the right child. Pretty straightforward, right?
Now for the big aha moment. This isn't just some random jumble of characters. Nope, there is a beautiful hidden pattern in here that we are absolutely going to exploit.
And that hidden structure, well, it's recursion. Think about it. The pattern for the entire tree is repeated inside the parentheses for every single child tree. This kind of self-similar pattern is like a giant flashing neon sign that screams, hey, you should probably think about this recursively. You know, a perfect way to picture this is with those Russian nesting dolls. The whole string, that's the biggest doll. And when you pop it open, what do you find inside? Smaller, self-contained dolls. And those are our subtrees. Okay, so let's put that idea to work on our example. We open the doll, we grab our root, which is the 4. And what's left inside? 2 totally separate substrings. Each one is a complete, self-contained child tree. But wait a second, that brings up a really important question. How did we know exactly where the string for the first child ended and the next one began? Well, that's where this clever little technique comes in. I like to call it the parentheses counting trick.
I mean, this is the whole problem, isn't it? As we're scanning through the string, how do we know for sure that we found the matching closing parentheses for that very first opening one? If we get that wrong, we can't separate the left subtree from the right one, and the whole thing falls apart. And here's how we solve it. It's actually pretty simple. We're just going to use a counter. We start it at 0. Then, right after that first open parenthesis, we start scanning. Every time we see another open, we add 1 to our counter. Every time we see a close, we subtract 1. And the very first moment, that counter gets back down to 0, boom, you found your match. You've perfectly sealed off the boundary of that entire subtree. Okay, let's make this real. We're going to trace this counter on our example string. Let's walk through it step by step. All right, we're scanning after the 4, and we see our first open parentheses. Counter goes up to 1. We are now officially inside the left child's world. Keep going. Another open parentheses. The counter ticks up to 2. This tells us we've just gone 1 level deeper into a nested subtree. Okay, now we hit a closing parentheses. The counter goes down, back to 1. We just popped back up 1 level. We keep scanning. We pass that 1, and then we hit its closing parenthesis. Our counter was at 1, we subtract 1, and bam, we're back to 0. That's our signal. That's the end of the entire substring for the left child. We found it. So now we have this foolproof way to isolate the strings for the children. The next logical step is, how do we actually turn those strings into trees? Just take a look at those child strings for a second. We've got 2, 3, 1 and 6, 5. Don't they look a little familiar? I mean, they're the exact same problem we started with, just smaller. So how do we solve them? And the answer is just so cool and elegant. We don't invent some new strategy. We just apply the exact same logic to these smaller pieces. We call our function again on them. That's the whole magic of recursion right there. You can literally see the chain reaction here. The first big call takes care of node 4, and then it launches 2 new smaller missions. It says, hey, you, go build the left tree from this string, and you, go build the right tree from that one. And then each of those calls does the exact same thing, breaking the problem down further and further until we're just dealing with single numbers.
Okay, so we've got the logic down, we've got the recursive idea, and we've got our parenthesis counting trick. Let's see how this all snaps together into just a few lines of actual code.
This table basically shows how our ideas map one-to-one with the code. Find the root's value? That's just grabbing the numbers before the first parentheses. Isolate a child substring. We just use the start and end points we found with our counter. Track the balance? That's a simple little count variable. And make the recursive call? Well, that's literally just calling our function. Maybe we call it DFS for depth first search on the new, smaller string. It's that direct. So, what are the big lessons here? First, when you see a problem with this kind of nested, self-similar structure, your brain should immediately start thinking recursion. Second, don't overcomplicate things. Sometimes a simple counter is all you need to solve what looks like a tricky parsing problem. And when you put those two together, you get this powerful parse and recurse pattern that you will see over and over again. And why does this all matter? Because this isn't just a brain teaser. It's a classic problem that really tests your fundamental understanding of trees, recursion, and string manipulation, all totally core skills in computer science.
And that just about wraps it up. But hey, here's a little something to think about on your own. We just went from a string to a tree. So, how would you reverse it? What logic would you use to take a binary tree and serialize it back into this exact string format? Give that some thought.